same team as the other Tom, so a different Tom. You might not notice the difference, same shirt and everything, but different accent. So I should give it away. And yeah, today I wanted to give a presentation on SageMaker automatic model tuning. And so this is work that I've done with an intern within our team called Martin. So combined work between us, and I'm going to show you applied to the domain of CFAR 10 training. So this is an image classification task. It doesn't really matter for this presentation the specifics of this objective, because the tools and techniques I'm going to show you can be used for a variety of different models. But here we're using it to train an image classifier, and we're trying to train it to the objective set out by Dawnbench. So Dawnbench was set up a challenge from the Stanford University, and they set an objective to train CFAR 10 models to get 94% validation accuracy or test accuracy. And CFAR 10, for those of you who don't know, we've got 10 classes of images. They're very small images, so it's 32 pixels by 32 pixels, and a reasonably small data set. So we've got 50,000 images in the training set and 10,000 images in the test set. The model that we're going to be working with for this, again, we don't need to look at too much of the details, but it's going to be a ResNet, and specifically a wide ResNet seems to give the best results for this challenge. And so that's what we based our work off. A really high level, ResNet is made up of lots of different convolutional filters, where we have a ResNet block that passes the residual, so instead of applying the convolutions to the information flow, you instead learn the residual, so the difference. And so you create another branch, and then you learn the convolutional filters on that branch instead. And a wide ResNet, you just modify that slightly, that you use more kernels, more filters in your convolutional layers. And that's essentially what you do. Here we're using a factor of 2. So that's from the models defined in the ResNet papers. We just multiply the number of kernels, and that seems to be giving better results in this challenge. And then a few other techniques we're using. So we're changing the learning rate schedule. This seems to be really important for this challenging competition. So typically you might have seen stepwise decay on your learning rate. This is for stochastic gradient descent algorithms, where you want to reduce the learning rate to get to a better optimum point. And here there's different policies and different strategies defined, and one that seems to give something called superconvergence is a one-cycle policy, where you just increase your learning rate slowly and then decrease it. And so we've added all those into our code. This is basically all a shameless plug for another talk that I gave that's on the MXNet YouTube channel that talks more in detail about these techniques, but we're using this under the hood for the training that I'm going to go through. So let's start with some basics, both for MXNet and for SageMaker. So, an overview again, MXNet. The main key points that I'd like to draw attention to here, specifically for Gluon, are the fact that it's really, really debuggable. So Gluon versus the module API, which is the main API before, we've now got the Gluon API, means you can literally set breakpoints in your network code and then step through and inspect the values of the convolutional filters for each iteration. Anything that you're interested in, you can visualize it as you train the network, so you can find any bugs in your code. And you get the flexibility, so you can actually condition your network. You can use if statements in your network. This is Python control flow, while loops, anything you want. You can do that with Gluon. So much more flexible. So they're the two parts that differentiate module to Gluon. Here's just a snippet of code I'd like to run through. This is Gluon 101, just for those of you who have not looked at Gluon code before. Just want to show you the main components. So the starting point for training your network model is getting the data. So in Gluon, the main objects that we're going to be looking at are having a data set, and a data set is responsible for delivering a single sample of data. And so here, because we're using CFAR 10, there's actually a Gluon data vision CFAR10 package that downloads the data automatically, it parses it, extracts it, so it will just return you the samples from the CFAR10 data set. There's a few other samples for you to work with there. We can apply augmentations, there's some transform operations. We've also then got the data loader. So the data loader is responsible for creating batches of data. So when we're training neural networks, we often want to pass batches of data through for better performance, and that's the responsibility of the data loader. Then we get on to constructing the model. So there's a model zoo in Gluon, so that's what I'm referencing here to get a ResNet 18, and then there's different variants. And in this case, I am not taking the pre-trained version because this sample code, I just want to show you how to train your own model. You can obviously take the pre-trained version with the weights, and you can just run that on images. That was trained actually on ImageNet for these computer vision models. So we've got something called a Gluon block, and that's the fundamental component in Gluon. You can combine blocks, you can call them just like functions, and it's going to take some input data and then return some output after going through different layers. And you can nest blocks in certain ways, so blocks can have children. And this is how you construct your own model and where you can put that architecture logic in. So now we have this block. Block has lots of parameters. So that could be weights of a fully connected layer, could be weights in the convolutional kernel. So we want to initialize those, and we can choose how to initialize them. So we're just using Xavier initialization. Next component we need to think about is what we want to optimize for. So this is where we can use the Gluon loss functions. I'm using softmax cross entropy loss, similar to what Oliver was using before. And then the last part we have to initialize is the optimizer and the trainer we want to use. So an optimizer, you may be familiar with different optimization techniques. Here I'm just using stochastic gradient descent. It's kind of a standard technique for optimizing networks, where it's got some hyperparameters. So this is where we've got a learning rate and momentum that I've just set. And then a trainer is a Gluon object that you provide all the parameters that you want to train, and then you say which optimizer you want to train those parameters on. So here it's just keeping track of all those parameters for us. So we can reference our network, call collect parameters, and it's going to work through all the children of that network, and they're all the parameters that we want to update. So now onto the actual training loop. So we've got two loops here. First of all, we've got our epoch loop. We're going to loop through the data 10 times. And then we loop through our data loader. So this is going to return our batches, because that's what the data loader was responsible for. We specified a batch size, I think it was 128. So data and label are both going to be of size 128. And then you have all the other dimensions of that data. Then the next part, we're going to actually transfer this data from CPU to GPU. So we can change its context, it's called. So we're just going to set the context to GPU, which we defined higher up. And you'll notice, yeah, the very top line on the screen now, we can set the context. So that's saying we want to run this all on GPU. And when we initialize the network, all the parameters of the network are also on the GPU. So that means we've got the data. Yeah, question?
I don't know if there's ever scope for this talk, but like multi-GPU, is it kind of abstracted away in this case, or you have to do?
So there's a few, so the question was about multi-GPU. A few changes that you need to make to the code, but there's not too many. Probably won't go into too many of the details now, but we're going to split a batch across all the GPUs and then do the processing on each of the GPUs. But it's not too much more, maybe 2 or 3 extra lines here. So we've moved our data and the labels to the GPU, and now we can do the processing. So there's something called AutoGrad, which is going to keep track of all the operations that we're doing, and it's going to build up this computational graph as we're going. So we have to tell AutoGrad that the steps we're going to take inside this scope we want to record and keep track of as part of the computational graph. So we can call our network on the data, and now that's just going to give us some predictions. So for CFAR10, that's going to predict the probabilities of each class for the 10 classes that we've got. And based on those predictions, then we can use our loss function, which was softmax cross entropy loss. We take our predictions, we have the labels, which are the true values, and then based on that, we can come up with a single value for a loss. And this is the thing that we want to be minimizing. So after we've recorded the forward pass, so just some annotations. We've got this forward pass, we do the backward pass, and that's going to then send the gradient all the way back through the network, and we can use the gradient for our trainer step, which you'll notice is here. So we take a step which is going to use those gradients based on which optimizer that we provided as part of the trainer. It's going to do stochastic gradient descent with the learning rate that we specified, and it's actually going to update all those weights and parameters that the trainer is aware of that we gave when we specified the trainer. And then we're just returning, we're printing out the loss. So that's really quick crash course into Gluon. How many of you guys have used Gluon before? Okay. Fair few. Much easier for debugging though. So just back to the breakpoint thing, I could have set a breakpoint here and then drill down into the net function and be able to inspect data and after it passes through its children blocks, which is super handy. Okay, so that was a super quick crash course on Gluon. Now the same for SageMaker. So SageMaker is a service in AWS that means you can get started with doing Gluon deep learning really quickly. So the first part is the fact that there's notebook instances that you can just spin up that have the likes of CUDA installed automatically, has a variety of different frameworks, one of which is MXNet. And so you can open up your notebook and then code away. The next part is the fact that you can do distributed training really easily. So you can construct your model on this notebook instance and then send it off to multiple instances that are spun up for you, and train the model much quicker. So it takes a lot of the complexity away, just being able to do these different training jobs. Then there's the feature that I'll be talking about in a bit more detail, which is the tuning, the automatic model tuner feature. So that's going to do some hyperparameter optimization for you on the models that you've built and started to train. And then when you're happy with the model, you can go ahead and deploy it, and it's going to automatically create different endpoints for you to use. And then you can fire predictions to that endpoint, either using your notebook instance or from external sources. So you've got the whole flow from building the model to deployment, which is streamlined. So in practice, when you're working with SageMaker, you'll start the notebook instance, and then from the notebook instance, you'll control the other services. So there's two main ways that I see people using SageMaker. First is through something called the SageMaker Python SDK, and there's similar ones. I think there's another one for Scala and Spark as well, but this is the code for the Python SDK. And then there's also functionality included in the Botto 3 library, which is a more general AWS library to control the different services, and so SageMaker is a part of that too. But this module and package is just really specific to SageMaker, so you can pip install it, but actually this is automatically installed on the notebook instance anyway, so you don't need to pip install it, just if you were using it elsewhere. But you can import it in your Python scripts, and then you can go ahead and create something called an estimator. So this is the key object in SageMaker SDK. There's different estimators depending on what frameworks you're using. So we're using MXNet for this case. And so we could call SageMaker MXNet and grab the MXNet object. The few parameters that we have to specify here. So this, we specify an external script. So this is where the training code is defined. So we're going to put it in a train.py file. We're going to specify the version of MXNet that we want, how many instances we want to train this model on. If we specified more than one training instance, we have to modify our training script a little bit to make use of those instances, but all the connection and the communication between those instances is handled for you, which is really handy. Then you define the instance type that you want to run this training script on. The instance type is going to be different from the notebook instance that you're running from, because it's going to spin up these instances for you. And then the role is to do with managing security, and then we've lastly got the hyperparameters. So you're going to write your training script in a way that it takes in these hyperparameters and uses them, so they're not hard-coded into your training script. And this is going to be really handy when we're doing the hyperparameter optimization, because we're going to vary these hyperparameters. So now we've created an estimator. The training doesn't happen at this point. It happens when you call the fit method. So here you provide the data that's going to be used for training. So again, the training script takes that as an argument and uses that to train a model. So here we're just specifying an S3 bucket, for example. So we've got, and now we've got a trained estimator after we call that. This function is usually blocking, so it's going to wait until this is completed, but you can also do asynchronous calls as well. But just for simplicity, we'll go for the synchronous version. And then with a trained estimator, you can deploy it. So the deployment is done through .deploy, you call that method. And this time we specify some different instances. So we might, for example, want to do our training on a P3 instance, which has got GPUs. And then for deployment purposes, to keep costs down and we don't need to service as many requests, we might choose something like a C5. So it hasn't got a GPU, but it's still quite effective and quite efficient in processing incoming requests. And we can then add auto-scaling as well to things like this for the deployment. So there's extra parameters that we can provide. And now we've got a deploy estimator, which is now called a predictor in SageMaker API terminology. We can then call predict on our predictor. So just creating some fake data, we can send that to the predictor with predict, and we'll get a response with our prediction back. So that data could be a NumPy array, it could be a Python list, it could be an ND array from MXNet. It's going to serialize that data, send it through HTTPS, do a GET request for a prediction, and then that's going to be handled on those instances that we've spun up, so the one C5 instance, and then return that to, in this case, the notebook instance. Oh, and then a little bit of cleanup, we can obviously delete our estimators and endpoints. So just to recap on that flow, we had the estimator that we defined and we configured. We can call the .fit method on it to fit, and that's actually going to be spinning up a training environment. So that's going to be on those instances, those P3 instances in our case, and those instances are going to be running Docker. So there's a container that's built with MXNet, because we specified we want to use the MXNet Docker, MXNet framework of a particular version, so it's going to be using those containers. And those containers are going to have access to the data that came from S3. That's where our training data was. And we define that when we call the .fit method. So this is going to train, going to return a trained estimator. It's actually going to save that estimator as a model in S3 again. So it's going to take that training data from S3 and save a model in S3. From the notebook instance, when we call deploy, it's going to create an endpoint, and inside the endpoint it's going to spun up a prediction environment. So this is where our predictions are going to happen. And again, it's going to be in a Docker container with the same specifications. And every time we have an incoming request, or we call predict, it's going to go through that endpoint into the prediction environment and then return the response. So obviously the important bit I haven't looked at here, I told you about, is what this train.py function has in it. So let's look at a sample of that now. So the way this actually interacts with the estimator is through a number of different functions. And these functions we have to specify precise names. So SageMaker API is looking for a train function, and it's going to call that function. And it's looking for a save function, so it knows how to save that model and save it in S3. So yeah, I've dotted out quite a bit of the code here that you need, but if we look at the signature for the train function, it's going to get a whole set of parameters for what the infrastructure looks like. So how many hosts this function has access to, how many CPUs, how many GPUs, and we can write our glue-on code to make the most of all those extra GPUs and hosts. We have the channel input directories, which is our input data. So SageMaker, when it spins up these training instances, is going to download that data for us, and we can have access to it. And then we've got the hyperparameters. So that's the key point, that we can use those hyperparameters, and we can access them by going what hyperparameters get, because we've got a dictionary, and we can have a default value if we don't specify it. And we can use those when we're training our network. And then the save function, just going to use the glue on method, which is save parameters. That's going to go through all the blocks, save all the parameters of all the blocks into a file, in this case called netparams, in the model directory folder. And that is, when training is completed, that's then moved to S3, that directory. So we put it in the right place. And then we've got a few other functions for when we've got the incoming requests. The transform function is what's called when we actually make a prediction. So we have JSON data actually coming through because it's a request through HTTPS. And then we can parse that into an ND array, pass it through our network, and then convert it back to JSON, and then send it back as a prediction. Okay, so that was the crash course on SageMaker. Now we can move to the fun bit, which is the automatic model tuner. So we've already seen in our script, we had a few different hyperparameters that we defined. So I like to think about hyperparameters, we can split them out a little bit. So it's the number of hyperparameters for the model. So it's things like the number of layers in your network, what activation functions you've chosen. So there's a whole suite of things we can choose there. We've got hyperparameters for the way that we optimize that model. So the method is a key thing we need to select. And then these methods typically have a learning rate because we want to determine the size of the step to make. Things like momentum depends on the optimizer sometimes. And then there's a variety of hyperparameters that we need to choose for the data. So batch size is a key part, or a key hyperparameter for neural networks. So we have to pick that. And we could also look at the different augmentations to apply. So when we're training models, we've got loads of hyperparameters and we need to choose sensible values for this. So this is where we make a distinction between what's sometimes called the inner loop training or optimizing and the outer loop optimization. So our training script or our training function was doing this inner loop optimization. So we have defined some hyperparameters and we've hard-coded them in the script or we've passed them through as parameters, which in this notation is the theta. And then so given those hyperparameters, we want to find the best model parameters, so the weights of the neural network, to minimize some loss. So in this case, we had cross-entropy loss. We want to minimize the cross-entropy loss. We want to find the weights that are going to minimize that. But that was all given the theta, given the hyperparameters. But we've got to work out what the best hyperparameters are. So that's where we've got this outer loop optimization part. And here we can parameterize what we're learning in terms of hyperparameters. So in this case, we're really looking to find the hyperparameters that minimize the loss of the network. So finding the best hyperparameters. And in this case, for the inner loop optimization, we had the gradient, so we could use gradient descent methods. But for the outer loop, we don't have this gradient, so we have to use some other techniques, more black box optimization techniques, to derive the best values of theta. And in some cases, you can pass the gradient through, but more often than not, for most hyperparameters, you can't do that gradient descent. So that's what we're looking at trying to do now, finding the best hyperparameters. Okay, and luckily, in SageMaker, there's some tools for us that we can use. So, similar code to what we looked at before for the SageMaker API. The difference being is I've got a few extra imports. So in SageMaker API, there's something called the Hyperparameter Tuner. So we can go ahead and import that. So SageMaker Tuner, we've got Hyperparameter Tuner, and then a variety of different data types. So we've got, in that list of hyperparameters we looked at before, we had different data types for each of them. Some of them are integer values, some of them are categorical, some of them more continuous. So we have objects from the SageMaker API for each of those. This is all similar to what we had before. In the case of defining our estimator, the hyperparameters that we choose here, so the number of epochs, are the fixed hyperparameters. So our training script might take a variety of hyperparameters. Sometimes we know the values for some of them, so we're just going to fix them in our estimator. For the ones that we don't know the best values for, we can create hyperparameter ranges. So here, let's say, we don't know the best learning rate, the best number of layers, and the best optimizer to use. So we're going to use SageMaker Automatic Model Tuner for those parameters. So learning rate, That's a continuous parameter. We can choose that. Here we're specifying bounds. We're going to choose a minimum value, a maximum value. We've got number of layers of the network. That is an integer parameter, so we're going to specify that. We're going to look between 8 and 16. And lastly, we've got categorical parameters. So that's just going to choose either SGD or Adam, as opposed to with integer, it's going to look at 8, 9, 10, up to 16. So they're all the different types that we can choose. Next thing we need to specify is the metric definitions. So we need to choose what to optimize. In this case, we'll see later on, we're trying to optimize the validation accuracy, because Dawnbench specified that we need to get 94% on validation accuracy. That's what we're trying to optimize. But we need some way of finding out what the validation accuracy was after it had gone to all these instances and inside the Docker containers done all the training. And the method for passing that data back to the hyperparameter tuning is through the CloudWatch logs. So you can, in your train.py function, write anything to logs. And here we're specifying how to parse those logs. So we define a regex expression that's going to work out where the validation accuracy is based on this, this little group. And then we have an idea what the validation accuracy is for every training job. So once we've specified how to parse the logs, we can then create our hyperparameter tuner. So the tuner takes the estimator, it takes the objective metric name, so this is the thing you're trying to optimize for, and then you say whether you're trying to minimize or maximize this thing. Because we want high accuracy, we're choosing to maximize. We've got the metric definitions, which is what we just defined, and then we can choose the strategy. So we'll look at the different strategies, but default and the recommended strategy is using the Bayesian approach. So we're specifying that as Bayesian. The last couple of parameters, we've got the maximum number of jobs that we want to run, and then we choose how many of those runs we want to run in parallel. So in total, we're going to try 100 different hyperparameter combinations, and we're going to try 10 of them in parallel, and then another 10, and another 10, etc. So the parallelization speeds things up, but it does have other effects. Yeah, question?
So how are the steps determined on the continuous parameter? You know, there's like very wide range.
So
does it dependent on the max jobs based on the others?
So they're looking, multivariate, so there's going to be an optimization across multiple dimensions here. We'll definitely come on to what this is doing after we've started one of these jobs, and then it might explain a bit more detail. And then estimator fit is what we called before. Here we call tuner fit, and that's going to start a hyperparameter optimization training job. So let's have a quick look at how doing that actually in SageMaker. So first of all, log onto AWS. Then we can start a notebook instance. So this is the first step of that process, that build part. So I've actually created one of these instances before, but to create a new notebook instance, you just go through these steps. You choose your notebook instance type. So typically the notebook instance type doesn't need to have a GPU, because this is just for controlling the resources, and so then you're going to spin up some other GPU instances, for example. So that could be like a T2, which is fine. And then you get all the usual options that you'd get with Amazon EC2, which is for your VPC, and any encryption. So you've started your notebook instance, and now you can go ahead and open that instance. This is going to open a Jupyter server. So to begin with, you won't have any data. I've cloned some repositories and actually used SageMaker examples. So this is, if you're just starting with SageMaker, you should definitely check out this tab, and you can preview and download these example notebooks. So for this case, we're going to run through one of the examples. Oh yeah, this is just an interesting thing that you may or may not have seen this before, which is the Jupyter Labs option. So by default, if you go to your instance, you'll get a pretty typical interface for Jupyter. But if you actually add lab on the end, you'll get a Jupyter lab interface. So it's a little bit easier for managing your folders and your files. So you get the interface on the side, you have access to the terminal, so this is where you can do your deploy. This is all on that notebook instance. So I usually prefer to work with the lab. And so this, yeah, is just an example of really similar to the code we just looked through. We're going to use the SageMaker API. We're going to create a tuner. In this case, we're actually training MNIST, so we have mnist.py as our entry point instead of train.py. This is using some of the symbolic codes. You'll see references to the module API, but that's just training a model and having functions to be able to save. We'll create our estimator. We define our hyperparameter ranges. So we're optimizing over 3 different hyperparameters here. Define our objective metrics as before. This is all really similar to what we just seen. And then lastly, create our tuner. So in this case, we're just going to train 9 jobs in total, and we're going to run 3 in parallel. And then we'll call fit. So that's going to start our training, our automatic model tuner training job. So in the interface, now we can move over to training, and we'll see hyperparameter tuning jobs. And we'll see we've got a new hyperparameter training job that's just started a few seconds ago. And so I'll leave that running in the background while I talk a little bit about Gaussian processes, and then we can reference that at the end and see how that's going. But really easy to start these jobs. Okay, so a little bit more on the theory. So I think this logic will be familiar to a lot of people. We're just going to step through all the way from grid search up to Gaussian processes quite quickly. So we've got hyperparameter space where there is a true underlying distribution that's hidden from us. So here, if we had 2 hyperparameters, we've got the learning rate and let's say the activations we're using as part of our neural network. There are true values for how performant that network is going to be. And let's just take the case where the best case is to choose sigmoid and for a learning rate between 0.5 and 1, so the red region. Like that's underlying, that's the best place to be. But we can't sample, we don't know this distribution beforehand, and it's really expensive to sample points in this space because our model could take ages to train. So the most simple approach is grid search. We're just going to sample that space. We're at fixed intervals across learning rate, and we're going to try it for all the combinations of the activations. And so we may get lucky and find a good point in that space, but more often than not, we're going to miss parts because we've had to do that spacing. The other problem with this, in this case, we're looking at 2 dimensions, but in reality, we're going to have way more parameters and way more combinations to search across. So this is just saying that we've got 5 options to search across, and we can have, if we have 10 hyperparameters, each having 5 combinations, we're just going to have like 10 million parameter combinations that we have to evaluate for that grid search. And if each one's taking an hour, it's going to take thousands of years. So not really an option. And another problem with grid search is the fact that not all hyperparameters are as important as others. So let's, for this case, say that activation doesn't really matter what activation we choose. Instead, it's just the learning rate that's important. So all of these true distributions are going to look the same. If we did grid search sampling, it's basically wasted effort. So we've sampled at the same points along learning rate. We found the same loss, the same model performance at each point. So yeah, lots of wasted compute there. Instead, which is the next step up, we could try something called random grid search. So rather than having this fixed grid approach, where we're trying all the combinations, we can specify up front how many times we want to sample this space. So we can just put random points across the 2, and we're much more likely for the important variables to sample areas where we have a greater model performance. So that's the intuition behind random grid search, and it's a really high benchmark to beat. So it's pretty performant. So what can we do better than random search? So random search, by definition, was just completely random. We were just trying random combinations. But we do get some kind of information here. We can see certain areas where we're getting more model performance than other areas. So maybe we could actually create a model of the model's loss. So some people call this a surrogate model, a secondary model, or a meta model that's trying to model that model loss. And what it's trying to do is approximate this really expensive to evaluate function, which was our h of theta. So given some hyperparameters, what is the performance or the loss of our network? And because that's really expensive, it's going to take us ages to evaluate, we want some other model that's really quick to evaluate. So we're going to try and approximate that model loss by some other function. And this is where the term Bayesian comes from in Bayesian Hyperparameter Optimization, is the fact that we want this approximate model to update depending on the data that we've seen previously. So here we're conditioned on some data that we've seen. We've evaluated at some points before. We know what the loss was at those points. So we can use that information to update our model and then have a better prediction of what the true model loss will be for other hyperparameters. So that's really useful to know. So this is sometimes called sequential model-based optimization. So we're looking at it from a different viewpoint now. We're just going to take a single hyperparameter for this case, which is going to be our learning rate. And on the y-axis, we're just going to look at accuracy. So accuracy is something we want to maximize. This dashed line is the truth, something, again, we can't see, but we want our model to approximate it quite well. But what we can do is we can take samples of this true distribution. So let's say we did our random search to begin with and we picked some certain points through here that we want to evaluate. So let's take those samples. For each of those runs, we do get a true model accuracy. For those hyperparameters, we can put some samples on that fit the true distribution. And then we want to fit our first model. So we want some model that's going to fit those points and then make predictions for hyperparameters in between the points that we've sampled. So we have some idea of what might happen between the two. Now we've got that model, we can use it to come up with our next point to try. So in this case, we'd want to pick the point which, according to our model, maximizes the accuracy. So we're going to take that as our candidate. And then we can evaluate at that point. So we now get the true model performance at that learning rate. And then we've got more data, so we can update our model, we have a better model, and we can use this model then to make the next candidate, the prediction for the next candidate, which would be here. So you can see how this is much more a reasoned approach to picking our next hyperparameter combination than just randomly searching through the whole space. And so to be a bit more concrete about, got a question? Yeah?
How do you make sure you don't sample in the local minimum?
So that is going to be determined by the model that you're using to fit. So if you define a range in which you want to search across, and depending on how smooth this model is, you might skip over the local minimum. But I hope, yeah, the Gaussian process model, you'll see that there's an extra feature that I think gets around that point. Because rather than predicting a single value, using the Gaussian process modeling approach, you actually predict a distribution at every point. So this is some kind of a concept of how confident the model is at every point. So this would be our learning rate along the bottom axis and our accuracy along the y-axis. And before we were just looking at creating a model that would predict the mean, which would be the blue line. But now our Gaussian process gives us a probability at each point. So we're more confident, this Gaussian process model is more confident of what the accuracy would be between these 2 points. So we've got a smaller confidence interval than it is greater than 8 in this case, where we've got a much wider confidence interval. So we're not really sure about what it is. Yeah, question?
So how do you actually build the Bayesian regression?
So coming on to that, yeah, in a bit more detail. Yeah, just to be a bit more concrete again, if we took a slice at a certain point, say 4, because we're using a Gaussian process model, we actually get a Gaussian distribution. So it's got a certain mean, it's got a certain variance. And we saw that this is where we're going to have a smaller variance, and in these areas we have a bigger variance. We've got a Gaussian distribution across the whole thing. So this is a little bit more on what's going on. So a Gaussian process is essentially a way of sampling functions from a multivariate normal distribution. So in this formula, we've got our x's, which are as a finite amount of points along our x-axis in the other example. So these are certain values for learning rate. Then we want to take a sample. If we say we're going to take 200 points across our x-axis, we're going to take a sample from a 200-dimensional multivariate Gaussian distribution with a given mean and a given covariance matrix. The covariance matrix shows the relationship between variables, how they, if one goes up, does the other variable go up as well, and it determines those relationships between the variables. So this is the really important point in Gaussian processes of how you define this covariance function. There's lots and lots of different ways to define the covariance function, lots of literature on it. You define the covariance matrix using what's called a kernel. So it's a function that takes 2 points along that x-axis and will return a covariance between those 2 points. So here we're just for a given xti and xtj, we're going to return a covariance, and that's going to be 1 point in our covariance matrix. So that's how we create that covariance matrix. And we'll look at the specific kernel that SageMaker is using for determining these for its Gaussian process. And then, yeah, we can take a sample from this distribution, which is going to return a single function through our space, hyperparameter space. If we go and simplify that equation just to 2 dimensions, this could be an example of our bivariate Gaussian distribution, where we've got our point x1 and our point x2. We don't know the values for those to begin with. This is before we have any data. This is just a Gaussian process at the very beginning. We're not conditioned on data that we've seen. And we take a sample from this multivariate Gaussian, and let's say because we've got the probability mass is highest in the middle of this region, we might take a sample. We've got one which is the x1 is 0.6 and x2 is 0.4. And the way that maps this point in multi-dimensional space to the representations we were looking at before with the x, or the learning rate along the bottom, is we take this point, and now this is how we plot it. So this isn't a continuous function, it's in discrete chunks. We've got x1 is 0.6 and x2 is 0.4. And in all the plots that we saw before for Gaussian processes, so for these plots, how you derive this is you just take lots of points. So instead of 2 points, we take a sample from 200 points. And it looks continuous, but it's been sampled. There's 200 points along that. And so instead of sampling from a bivariate case, that's sampling from 200-dimensional space. Now, let's take the case where we had data. So we've evaluated at a given point. Let's say we evaluated at x1, and our accuracy was 70%. Now we want to condition on that value. So we know that x1 is 0.7. So given that, what is the probability of drawing a certain value for x2? So this is a different learning rate we're dealing with. For the case that I've shown here, our covariance was 0 between x1 and x2. So knowing that x1 was 0.7 doesn't change a thing for x2. x2 is still the same distribution. And so there's a sample that you take from there, and in this case we could take a sample and it's 0.6, so nothing's changed. But very often the case, you're not going to have this situation where the covariance is 0 between all the functions. You want to have some covariance. So this would be a case where the covariance between x1 and x2 is negative. So as you increase x2, you're more likely to decrease x1 and vice versa. So they're inversely correlated in some sense. So if we had the same data, we evaluated the model at x1 and its accuracy was 70%. What we do is we take the conditional probability given x1 equals 0.7. And because these are Gaussian distributions for given kernels, we can analytically work out what those formulas should be for the conditional probabilities. And in visual, if you want to think about it in visual terms, it's taking a slice through this multivariate Gaussian distribution, and then you're using this as the probability distribution for your point x2. And because we had that inverse relationship, the covariance which was negative, it's actually shifted the distribution for x2 now. They're not independent anymore. So if you look at the distribution, it's actually shifted down, so we're more likely to sample lower values of x2 than we were in x1. And yeah, just to go back, this is an example of a single function. So that's a single sample from our 200-dimensional multivariate distribution. And if we were to sample this lots and lots of times, on average, the functions we're highly likely to sample functions that go in between these confidence intervals, but there is a chance, because these are Gaussian distributions, that every now and again the function will go outside these confidence intervals. And so we can use this as our model for this. The reason why we're using these is that model of the model objective, which was accuracy, because it's costly to evaluate. So for SageMaker, the kernel function that I haven't really talked about much is something called the Mattern kernel. So points close together, so learning rates that are similar, have a covariance that's quite high. And for learning rates that are far apart, the covariance is lower. So this is embedding a smoothness in our function. And depending on how we fix these parameters of the Mattern kernel, in this case, we've got V, that's going to determine how smooth we have these Gaussian process functions. Yeah, question?
So this is only for continuous hyperparameters, right?
Yes, yeah. So you can create kernels for other types of data as well. You can have integer values, and then you can have kernels for categorical values. But that's all needs to be included in your kernel. And there is a later stage, everything gets mapped to what's called a hypercube. So things are mapped into a continuous space in some cases.
So what would be the proper way to do categorical variables in treatment?
So, but if you're using Gaussian process, the recommendation is keep things as numerical if you can. So if they are true categories, then you can provide them as a categorical variable. And I'm not too sure on the specifics of which kernel they're using for categorical variables, but things are mapped to a hypercube, so they do one-hot encoding to your categorical variables, and then they apply a different kernel for that and combine it with the Mattern kernel for the continuous variables. But don't bucket stuff and then use them as categorical variables. If it is truly a continuous variable, keep it that way.
So is this a covariance between hyperparameters?
Yes. Yeah.
Which doesn't or does depend on the specific model you're using? So you know what I'm saying? So
yeah.
If you imagine, right, so even if you have the very same set of possible hyperparameter values, depending on specific models you're using, the function value will be totally different, which means the shape of the function will be different, blah, blah, blah. Right.
Yeah, this is really this V that we're using for the kernel is a hyperparameter of the hyperparameter optimization. So, but there's a good default that I think, yeah, so it's 5/2. It makes the calculations much simpler, the functions reduce, so much quicker to calculate. Okay. Yeah.
Does SageMaker support just deep learning models?
No, so you can, there's a number of different models that are included in SageMaker. So nearest neighbor search, for example, is one of them. There's a few other different ones that are separate to all the framework functionality that's included. So you can use them. Yeah. Question?
So in this process you have a Bayesian regression, right? So you have like prior Gaussian distribution and then you try to get the Gaussian distribution, right?
Yeah.
How do you specify the prior parameters? Can you somehow specify them or use default prior parameters?
So the
Parameters of prior distribution, prior distribution. So you have prior distribution Gaussian, then you apply Rice rule and have the second cluster distribution after Gaussian, right?
yes, the prior is defined by the kernel that you pick. So depending on how you define that, that's going to, what you choose for this kernel function is going to derive the covariance matrix, and that is the main component in your Gaussian process. You've got the mean as well, but I think the mean is dealt with separately as just some kind of linear model, rather than the Gaussian process having to learn that. In this Gaussian process, you set the mean to 0 and then learn the mean with a different model. So,
Can you use anything except Gaussian distribution in the parameters when you try to solve?
So for SageMaker, you have grid search and random grid, I believe, and then this is the Bayesian search, which is the default and more recommended. Okay, so just want to quickly talk about what we do with this distribution, if I've got time. So we have this probability now for every point across all the learning rates. And we use something called an acquisition function to pick our next candidate point given this posterior distribution of functions. So we can use this as a criteria for selecting the next candidate. This function depends on the best hyperparameter that we've seen so far. So we'll see that in the functions. And it controls the balance between exploring new points and exploiting points that we know do really well already. So the very first, or the most basic way of looking at this, we've got this Gaussian process that defines a Gaussian distribution at every point. So these are all our learning rates, remember, and this is our accuracy, and we want to find maximum points. We've evaluated at 3 points already, and this learning rate gives us the best accuracy so far. So we want to choose another point, another learning rate that has the potential to give us the best improvement. So the first thing we can calculate is the probability of improving. So we're going to use this as a threshold, and then we're going to look at the probability distribution above that point for every point along our x-axis. And so for x3, for example, we could look at the Gaussian distribution and say we have 70% of the distribution is above that threshold, which was our current best. So the probability of improvement is 70%. And so for these two cases, let's say we've got point x1 and x2. Well, x2 will actually be chosen because there's more probability mass above the threshold than for x1. So that we can see this is really exploiting the points that it knows do well. But an alternative to add more exploration is to look at the expected improvement. So we define improvement as any accuracy above the current best, and then we want to look at the expected improvement. So this takes into account more of the scale or the magnitude of being able to improve. So for this case, x1 will actually be picked above x2 because we're ignoring anything below the current best because that's not an improvement. And actually the improvement is 0, so this will always be pushed to 0. And then when we're doing the expectations, we're taking what's the average improvement that we're going to make, which could be something like 0.3 in this case. But here, for this case, ignoring this, well, our expected improvement, even though we've got more probability of improving, the actual improvement is less. So we'd prefer to take points like x1 than x2. And we can evaluate this, this number, expected improvement, for all values of x, because these are Gaussian processes and Gaussian distributions, we can compute these quickly. This is what we could get. This is our acquisition function. for all points along our x-axis, and we want to take the point that gives us the maximum value of whatever acquisition function we've got. And so we can step through, pick the best point one after a time. And last point is just the fact that we can parallelize this through something called Thompson's sampling and take random draws from this distribution and pick the maximum point from each one. So I think I'm going to wrap up there. But you can, based on the results from the SageMaker hyperparameter tuning, you can then analyze your results as well and plot different graphs of all the variables against the objective metric and then determine the best values to use. And SageMaker is going to give you the best value as well. Yeah, question?
So you pick the model from the model's array,
Yeah.
assuming that I had certain nonlinearities that are well known. Suppose I'm like this funky researcher who comes up with my own thing. How customizable is SageMaker in order to be able to find my own hyperparameters for the op that I came up with? For a
Yeah, so if you write your script in a way that takes these hyperparameters, you can construct a different model completely and then optimize that using these techniques.
Is it like, is the so this is a bit, in my understanding, like hyperop, right?
Yeah, use a different technique. So I think that's using TPE, this one's using Gaussian processes.
Okay.
Yeah.
But is the code for SageMaker open source where you have a community, a certain committing to it, or would I have to wait for someone on the SageMaker team to support?
So it is open source. There's a Git repo with the SageMaker API. You can look at the code, and then you can make feature requests on that Git repo, I think.
One last question?
Right, so you mentioned at first that the objective was to reach 94% for step part. So is that the way to reach this by?
Yeah, so this was the technique that we used to train that model. And yeah, the results of all this hyperparameter optimization, I'm going to show the results, but we ran out of time a little bit, was the fact we managed to train CPAR10 model to 94% accuracy in 4 minutes on a single GPU, which was the quickest on record to our knowledge. There's quicker times if you have multiple GPUs. I think 8 GPUs did it in about 3 minutes. But on a single GPU using this hyperparameter search, managed to find hyperparameters. So there's a GitHub repo with the code for it, but it's not published. Particular paper or anything.
Published in the blog.
Yeah, not blog, that's right. Oh, yes, sorry.
Yes, we have a blog writer, but it's not published in
Yeah.
conference.
Thank you. Thanks.